I've learned so much over the past 2 days. It's been great. Thank you. My name's Justin.
I'm Chris.
And we are here today to talk about a question that we have come up against a lot over the past 2 years as at the company where we work, we have been adopting 3D tiles. Just to preface what is coming in this talk, we are going to be giving you more questions than answers, probably more problems than solutions, just to frame what's coming. That's the vibe. As we have adopted 3D tiles over the past 2 years, we realized that this question we were having was not one that we were not the only ones who were having this question. There were lots of other people on the internet who were asking the same question. So the question that, at least it felt to us like everyone was asking, is how do I compute geometric error? Raise your hand if you are familiar with geometric error. Okay, a few people, not everyone. That's good because it means all the slides we've made are not wasted. So we're gonna talk about what geometric error is and why it matters and how it affects the way that your tile set actually looks when it's on screen. But before we do that, we should say a little bit about what we do and why we're here.
Yep. So that went forward 2 slides. So we are from a company called Sensat, based just across the pond in London, and we largely want to make the world a better place than it currently is. A slightly shocking statistic that you may not be aware of: over a third of global carbon emissions come directly from the construction industry. And so one thing that we're trying to do is allow construction companies to make better decisions across the world, to whether that's routing power lines, whether it's rolling out 5G networks, building major civil infrastructure. And in practice, what that really means is taking both reality data, which is data about what exists in the planet already. That might be point clouds, that might be orthomosaics, that might be photogrammetry meshes, and combining that with the CAD models that they have of the things they're trying to design and build in order to prevent them from making crazy decisions. For example, instead of just crazily estimating the amount of material they might need and then just throwing the rest in landfill, they can get much more accurate measurements. Or equally, starting by drilling massive piling holes in the ground and building half the foundation of the building, and then someone comes along and says, did you know that this building will be in breach of regulatory requirement XYZ because it needs to be at least 6.2 meters from this fence?
So to make that happen, we bring different types of data together, as Chris said. We bring together reality data with GIS data and CAD models, and when we do that well, it renders smoothly. Our users are able to zoom and navigate and move through, and everything just looks right. So that's the dream. This is another kind of moment where it's working pretty well. There's a lot of stuff in here, but it's pretty smooth. But sometimes it's not so good. So you can see here this building. So this building over here looks fine, but this building is not. It's the levels of detail are not coming in at the right time. The low levels of detail are coming in too early, and as a result, it looks kind of like an abstract geometric sculpture, which is not what we want. We want it to look like a building. So to unpack why this is happening, why this can happen, we're gonna take you all on a little deep dive into some of the internals of 3D tiles.
So the very, very simple and cut down explanation, to take the entire tree of the 3D tile set, which is essentially a hierarchical set of level of detail, That itself is a tile set, and then each node within that tree is a tile. Each of those tiles will contain some geometry and some metadata about that geometry. And the hierarchy that's present allows us to effectively select which level of detail we need to render at a given point in time to try and make the best user experience without impacting performance too heavily. I think that's fine. So the reason that we do that, if we go back to sort of a basic principle of rendering, what are we trying to do? Well, we're trying to render as much as possible on screen, making it look as good as it can for the user, but we don't want the user to realize that we're actually playing a bit of a trick on them and not rendering everything in full detail. Luckily for us, there is a metric called screen space error that we can use to determine whether or not a level of detail is sufficient for the given view of the user.
So screen space error is a way of measuring the difference between the kind of true geometry, the full level of detail, and the like the simplified thing we're showing on screen. So just to maybe translate this a little bit, this is kind of analogous to in 2D mapping the way you have a sort of pyramid of tiles, and you have maybe one tile at the top level, and then 4, and then 16, and those levels are just numbered. So you have level 0 all the way down to zoom level 14, and that works nicely because you're always perpendicular to the map surface. Not always, but often. As soon as you tilt that surface, and definitely when you're going full 3D, you have to kind of leave that the idea of simple levels of zoom behind, and instead come up with this much more granular way of calculating for every geometry what level of detail it should be rendered at. So screen space error is measured in pixels. It's worse, larger is worse. So more screen space error means that it looks worse. And very importantly, it's a relative quantity. So it depends not just on what you're rendering, but it depends on where that thing is on screen. So it's not just about the geometry, it's where it is. So just to give a quick example, were you going to take us through this? Should I? Okay. So on the one side of the screen, we have the full detailed geometry. On the other side, a simplified version of the same geometry. And then here, we're rasterizing it. This black here is kind of a representation of what screen space error might be like. So it's a measurement of the divergence between the full level of detail and the simplified level of detail. And you can see here that that screen space error does depend on where it's rendered on screen. So imagine that we're zooming out here. This is getting smaller. And as it gets smaller, there's less divergence between the simplification and the full level of detail until it pretty much disappears. And if we go to the next one. So if we set, say, a threshold of 2 pixels, then we have our full level of detail when we're up close. As we go back, maybe we keep our full level of detail into here. Remember, I think here the screen space error was 1, something like that. But eventually, we fall back to a simplified level of detail because that lets us fit more on and make good use of resources. There are other ways that we could allocate our screen space error budget over the screen, though.
Yep. So, for example, to take a lesson from biology, we can use something called foveation to spread the screen space error non-uniformly over the screen. So typically the user is going to be focused at whatever is in the center. So we might wish to allocate more screen space error budget to the center of the screen. So in this case, you see that we would maybe render the high detailed curved line in the center, but then revert to the lower levels of detail on the outer edges of the screen where the user's probably not paying as much attention. And I believe this is an example of exactly that. So one of the things we're doing here as well is that as you see we're zooming around, we start by loading not just what's closest to the camera, but what's actually at the focal point of the camera in the center of the screen, which is a little bit more complicated than usual. And a lot of libraries and things will typically just load directly from the closest to the camera, which is usually what's right underneath you going away, and that creates an interesting effect.
So we have found that especially when users are navigating around, all those interactions are taking place at the center of the screen. And it's really hard and really annoying when you're trying to make lots of interactions. Say you're dragging, you want to move the camera around, but there's no detail there, and all the detail is at the bottom of the screen. So all this is just to say there are different valid choices that one can make about how to treat the screen space error. But I guess the basic thing is screen space error is this useful abstraction for bringing in levels of detail at different times. If we were to calculate it the way we've shown up here, though, it would be quite expensive because we were sort of showing as a schematic, like you have your full level of detail, you have your simplified level of detail, and you're comparing them based on how they're actually rendered. Now, in practice, we don't want to render the full and the simplified level of detail at the same time. We don't even want to render, say, the full level of detail onto a buffer that's hidden and then compare, because that would defeat the whole purpose. So instead, there's a kind of shortcut that the 3D tiles spec has defined called geometric error. So geometric error gives us a nice way to sort of approximate the screen space error for a level of detail. You want to take us through this? Okay. Geometric error is measured in meters. So remember, screen space error measured in pixels. Geometric error measured in meters. Again, larger geometric error is worse. It means it's not going to look as good. And importantly, geometric error is absolute. So it doesn't matter how the object is being viewed, how the geometry is being viewed. Yeah, it's absolute. Yeah. So this just shows how geometric error is used. So instead of actually rendering and comparing different levels of detail on screen, we use this geometric error and scale it based on where the geometry is on screen. So here the geometric error is it's too large. The quality is going to be very poor. Here, still too large. We don't want to use that simplified level of detail. But up here, it's small enough that we're ready to bring in the simplified level of detail.
So that's a bit of a crash course in what geometric error even is, why it exists. But the natural question you might be asking is, well, okay, but how do I calculate it? Why are we sat here talking? What's the point of this? Well, it's actually quite complicated because not every single type of geometry is the same. So the way you might want to calculate the error for a point is not necessarily the same as a line, is again not necessarily the same as a mesh. And equally, the spec is quite permissive in what it allows, and the natural recommendation around seems to be that you can kind of calculate this however you want. You just, here's some good ways of making an approximation, but good luck. So we thought we'd share some of the ways that we've personally calculated geometric error, starting from the left here. So for lines, we can calculate something called the Hausdorff distance, which is essentially the furthest point from the original model to the closest point in the simplified version. So in this case, Along this simplified orange line, the furthest point, or the most errorful point away in the original model is up here. And so our Hausdorff distance is just the distance between those two. And then this is where it starts to get a little bit messy. For points, we can make a fairly safe assumption that usually as the level of detail decreases, we sample fewer of the points from the original set. And because of that, the average distance between those points typically increases with the rate at which you sample them. So minus a little bit of magic dust of scaling factors, we can pretty much use this average distance between the points. And unfortunately for meshes, it gets even more complicated. The simplification algorithm that we personally use allows us to provide a percentage simplification. So if the mesh started with 100 vertices and we pass in a simplification target of 0.5, we will end up with a version of that mesh that contains 50% of the vertices of the original mesh. And for some reasons that I won't delve into the details of, we can guarantee that the error of that will be less than the length of the bounding box diagonal, as you see from this white line on the diagram, multiplied by the simplification factor. And then again, we provide a little bit of extra magic dust. And you might be wondering why that exists. And that's largely because these three different algorithms will produce values that are on very different scales. And because geometric error is fundamentally an absolute metric and has a unit in meters, we need those values to be quite close to one another for similar levels of error. Otherwise, we start to see cases like we saw in the original example again here, where the geometric error that we've been given gets converted to a screen space error that tells the renderer, hey, it's okay to replace this super high-res model with this amorphous blob of triangles, when actually this is really visible to the user and we shouldn't be doing it.
Yeah, so one problem we have is that within the data, across the data that we ingest, there are a bunch of different ways of calculating geometric error. And if they don't match up, then we can end up with certain types of data popping in too quickly, or someone mentioned earlier tiles being blurry. That's another thing. That's another way this can manifest. So here we've got different types of data, and we're calculating geometric error in all these different places, really kind of different subsystems. But it's actually even more complicated than that, because we are not only serving data that we ingest ourselves, we're also serving data that like tile sets that are produced by third-party tools we use. So that's something where we're hosting the tile set ourselves, but we don't control the way it was produced. And then we do not currently, but would really love to and plan to work over the next few months to integrate third-party streaming tile sets, like the Google API that that Travis presented earlier. So that sort of magnifies the problem, because we don't have any control over the scale of those geometric errors in those tile sets, or really the structure of those tile sets. And what we found in practice is that different renderers, as much as we would like, and I think the spec would like, for renderers to be agnostic to the source of a tile set. So as long as it conforms to the 3D tile spec, it doesn't matter which renderer you're using, it should just work. What we found in practice is that the tile set structure, like how large the tiles are, how deep the tile set is, whether you have lots and lots of small tiles or a smaller number of larger tiles, that can affect rendering quality in different renderers. Some renderers are more tuned for lots of small tiles. Others are more tuned for larger, fewer tiles, and they also will set different screen space error thresholds. So this is the problem we face. And when you zoom out even one step further and think about the whole ecosystem of lots of different people producing tile sets, and also lots of different renderers. It becomes kind of a little bit of a messy situation, where some tile sets produced by some providers work great in some renderers, but not others. So yeah, not the happiest situation.
Yeah, so today, 3D Tiles is, as we say, a fantastic first-party format. It has been very helpful for us to implement. We've had great success mostly implementing it, but we have struck some issues with it. So as Justin was just saying, in order to create a good ecosystem around it, we really need some way to standardize geometric error in some form. Otherwise, it's really, really difficult to encourage widespread adoption across the ecosystem. So there are kind of three things that we would probably propose here. The first is something that we are absolutely guilty of ourselves. Make no no false assumption about that. But firstly, we need to kind of ensure that geometric error is always representing some real world quantity. And with these sort of like magic pixie dust scaling factors, that loses all meaning entirely. Secondly, we would love to collaborate with other people who produce tile sets in order to understand how they personally calculate geometric error for points, for meshes, for lines, whether or not we can learn from one another and kind of agree on some consistent or standard way for doing so, whether that be specific algorithms or ways to convert from one algorithm to another in terms of the output tile set that's produced. And thirdly, we kind of see a wider opportunity, and sort of linking it more back to the people in this very room, for Lotus.jl in particular to become perhaps a bit of a reference implementation and maybe anchor the rest of the ecosystem to say, hey, look, this is how you do it. If you want to go and build your own, you can, but here's a great place to start, which doesn't really seem to be something, at least that we've found, exists right now.
Yeah, so I was having a conversation earlier with someone about, I think Martin, about adding better support in DeckGL for globe CRSs and for transitioning between globe and flat CRSs. That is something we have talked internally about working on over the next few months. So definitely where there are places where the things our customers are asking for would benefit the broader ecosystem. That is definitely something we would be excited about. So yeah, we're excited about the collaboration opportunities for improving the whole 3D Tiles ecosystem. And with that, thank you all. Thanks for having us. We wanted to say a quick shout out to all of our colleagues who are not here with us today, but who we've learned a lot from, and open it up to questions from you all. Any questions?